Hello, y'all. Welcome to lesson 105 of my DP chemistry curriculum. Today we're going over reactivity 3.1.16 and 3.1.17. In 16, we're going to talk about how a buffer solution is one that resists change in pH on the addition of small amounts of acid or alkali. For 17, we're going to talk about how the pH of a buffer solution depends on both the pKa of its acid or base or pKb and the ratio of concentration of acid or base to the concentration of conjugate base or acid. And we'll solve some problems with that as well using our icebox equations and our pHs and equilibrium constants. So we mentioned buffers a little bit when we were talking about weak acids and weak bases and their titration curves, but what is a buffer solution? Well, a buffer is really just a solution that resists changes in pH, specifically when you add acid or alkaline. When acid or alkali is added. So it allows the pH to stay pretty consistent. We use this often. We can use it to, as it does, regulate pHs in places where we need to regulate pH. We often use it to calibrate pH sensors or pH meters. So those are pretty good. Um, we can use it for many other things, but this is generally the two I think about. Now, they work because of Le Chatelier's principle. That's a, whoops, Chatelier's principle. So they shift their shift equilibrium to resist change. We're going to go into that a little bit more later, but I think the best way to do this is by looking at an example. So one of the places where we have buffers to help regulate pH is our blood. In our blood, we use carbonic acid. That is that is formed by the carbon dioxide that we actually produce as part of our respiration. So carbonic acid in blood is a use of a weak acid as a buffer. So carbonic acid is H2CO3, and when it reacts with water, it produces, in equilibrium, hydronium ions plus bicarbonate or hydrogen carbonate, HCO3 minus. So as we increase the acidity in our blood, what we'll actually do is it will react with our bicarbonate, producing more of that. And as we add alkali, it will remove our hydronium, converting back into bicarbonate. So whichever way, this solution can resist that change. So it will just shift right or left to specifically remove or add hydronium to solution, depending on what we need to do. And that is a product of Le Chatelier's principle in this equilibrium. So when we look at buffers, well, what actually makes them? So we'll take a moment to look at their composition, as well as how to make a buffer. So these are based on weak acids or bases. And we know that weak acids and bases partially deionize or dissociate. And that's the key thing. These are therefore the primary components of buffers. But you may realize that as a primary component of buffer, we know that our weak acids and bases, when we say partially dissociate, we mean they kind of barely dissociate at all. That's why in ice equations, icebox reactions, we can pretty much remove the concentration taken away from our initial concentration. It's so little. Our Kas and Kbs are so low. So that's really only half of it. In addition to resist change, we have to add in, or the buffer should include the conjugate form. And so we need the conjugate form in approximately equal amounts. So what do I actually mean about this? Well, when we look at our blood, what this means is to be a good buffer, we should have pretty equal amounts of both forms of this. So as we add more of one, we can shift over, and as we add more of the other, we can shift back. If we don't have equal amounts, then that balance isn't well realized. We actually discussed this back in titrations, and we'll come back to it in a little. So as we mentioned, weak acids or bases. I'm going to usually refer to acids in this as we're going to look at more acidic buffers and basic buffers, but it's still pretty much the same. But weak acids and bases don't ionize enough to effectively buffer. So therefore, what we're going to do is add in that conjugate form. So when we look at our weak acid, for example, HA, turning into H plus and A minus, what we're really saying is that there is not enough A minus. We're going to have to add to solution. A great example of this might be with vinegar or acetic acid or ethanoic acid, three names for the same thing, CH3COOH will deionize into H plus and ethanoate, CH3COO. And what we need to do is we can add more by using a salt. So we talked about how some salts can be acidic or basic. And what we have to do is that when we add the salt, we must be careful to not add an acidically or an acidically active cation. So for example, we can use something like sodium, but we can't use something like ammonium. So we might add sodium ethanoate, which will always dissociate into sodium positive ions and ethanoate ions, COO minus. So we know specifically we are adding that in. However, we also know that sodium ions will not uh, accept, or not accept, will not steal hydroxide. Uh, what we've referred to it is it will not hydrolysize. So it won't break water apart to create hydrogen and hydroxide and then bond with that hydroxide. So we know sodium is fine. We talked about that in our salts lesson. So how do we make the perfect buffer? Well, an ideal buffer, which might be a word that we've heard before, will have equal amounts of both acid and conjugate base. Or if we're referring to a basic buffer, then we could also say or base and conjugate acid. So any way we can make those equivalent amounts will be an ideal buffer. So we can just add two solutions together. We could add, for example, going back to our ethanoic one, we could add 0.1 mole decimeter cubed of ethanoic acid. And maybe we'll do like 10 mils. And we then add that to 0.1 mole decimeter cubed of sodium ethanoate. And we would also do 10 mils. We can change that up. Maybe we do 0.05 and 20 mils, but the same thing is we still have the same amount of moles either way. So you want to make sure that your moles of both the acid and conjugate base are the same. You want the same amount of moles of each. So this is how we can create a buffer. Another way to create a buffer is we can also create buffers through neutralization reactions. And what I mean is if we have some acid and I'm going to go, or some weak base, we'll set up our titration and we're looking at our pH curve here. And we'll do volume of strong acid added. And we look at our pH curve. If we're starting with a weak base, maybe we're starting somewhere around 12, this is what our pH curve looks like. Let me try that one more time. All right, a little bit better, not great. We actually know this as our buffer region. And right here is our equivalence point. Which means at halfway through that, right here, we are at our half equivalence point. And part of that half equivalence point is at half EQ or EP. At that area, we have equal concentrations. Whoops, equal concentrations of our base and our conjugate acid of that base. And so that would also be an ideal buffer. So by knowing what we're using, we can just stop our reaction or stop our titration at our half equivalence point, and then we have created our ideal buffer solution. So there's a couple ways to do it. Now, in addition to this, how do we actually find the pH of a buffer? There are a couple ways to do it. Well, there's one main way to do it that we'll work on, but we first have to know what it's dependent on. And we know, as we read at the beginning, that the pH is dependent on two things, the pKa or pKb of that given acid or base, which also means the pKa or pKb also means the Ka or Kb. We're talking about the same value at that point. And finally, also the relative concentrations of the weak acid or base, depending on what we're doing. So not just the concentration of those, but also and the conjugate. So we need both. So what does that mean? How do we find the pH of a buffer using these values? Well, one of the best ways to do it is to just do an example, but before we do that, to calculate it, what we need to make sure we're remembering is that when we are calculating pH of our buffers, we want to make sure that we are accounting for the change in our concentration. So this is our standard reaction, but when we oop, add HA solution to a minus solution, we have a new volume. So when you're creating a buffer, either via titration or by adding the salt to the acidic solution, we have a new volume. A new volume means new concentrations, which means you have new concentrations to plug into your Ka formula where you're using these individual concentrations as you're calculating the concentrations of each. So let's go ahead and with this information in mind, do an example. So in this example, we're going to prepare a buffer, and we're going to do this by adding 0.020 decimeters cubed, so 20 milliliters of 0.10 mole per decimeter cube inverse of carbonic acid, H2CO3. We are going to add that to 0.010 decimeters cubed, so 10 milliliters of a same concentration salt of carbonic acid. In this case, we'll say sodium bicarbonate or sodium hydrogen carbonate, baking soda. We know from our given that the Ka for carbonic acid is 4.47 times 10 to the minus 7th. So what we're going to do is calculate pH. According to what we just learned and what we're trying to keep in mind up here, if we're adding two solutions, we have a new volume. So let's go ahead and first calculate our new volume. It's kind of easy to do that. We have 20 milliliters plus 10 milliliters, that's 30 milliliters. So that's going to be 30 mLs, which we're going to keep our decimeter notation, 0.30 decimeters cubed. Then we need to calculate our new concentration of carbonic acid. Oops. So we're using C1 V1 equals C2 V2, and therefore we want our new concentration C2. So we'll divide the whole thing by V2 on both sides. And we'll find that if we take our original concentration, 0.10, multiply it by our original volume, 0.020, divide by our new volume, 0.030, we'll get our concentration equivalent to 0.0667 mole per decimeter cube inverse. Now, we're going to do the same thing with our sodium carbonate, or sorry, sodium bicarbonate. In this case, I'm going to stop referring to the sodium. I'm just going to be looking at the bicarbonate ion, CO3 minus, which sodium bicarbonate will fully dissociate. And I'm going to just skip straight to the step where we use this equation. So 0.10 times our original volume, 0.010, divided by our new volume, 0.030. And we will get a concentration of 0.0333 mole decimeter cube inverse. All right, those are our concentrations. And now we can actually begin our ice table. So I'm going to go ahead and write our equation for this acidic buffer. H2CO3 dissociates into hydronium, or sorry, not hydronium, just H plus hydrogen carbonate. And we will divide it down. initial change equilibrium. Our initial is 0.06670 and 0.0333. These are all concentration values, which is what we have to be wary of when we're doing an ice table. We're using concentration. We will lose some amount x as it dissociates. We will gain some amount x. We will gain some amount x. We will get 0.0667 minus x, and 0.0333 plus x. Now, what we recognize is that in this equation, we have an incredibly small Ka. When we have a small Ka, we can disregard x when we are adding or subtracting it by numbers far above its magnitude. So we can just remove x from this equation on both of these sides, and we can set up our Ka. Ka is equal to our H plus value, which is x, times our carbonate or bicarbonate value, which is 0.0333, divided by 0.0667. What you may recognize is these essentially cancel out to 1 over 2. And so what we actually get is Ka is equal to x over 2. And our Ka is 4.47 times 10 to the minus 7, meaning that x is approximately 8.94 times 10 to the minus 7. That x is our concentration of hydrogen. Therefore, we can take the negative log base 10 of 8.94 times 10 to the minus 7 and find a pH that is approximately 6.05. So this is kind of how we go through these equations. It takes a little bit of math as we go through. You have to be comfortable with your ice tables as you do it. But if you use diligence and you make sure to take each step carefully, it becomes quite simple to do over time. If we are talking about a basic buffer, I have good news for you. A basic buffer is the same. You can use the exact same process. The only difference is you usually end with a pOH value. So what you have to do is convert that to a pH, and what you just do is take 14 minus pOH equals your pH value. So other than that, you can use the exact same process, the exact same ice tables to do these calculations. All right, the last part of this incredibly long video is what happens if we dilute buffers. Well, there's good news and bad news. The first thing is when you dilute a buffer, the ratio between the forms stays the same. That's the good news. The bad news is with lower concentrations, it is going to be less resistant to change. So your buffer won't be as resilient. Your buffer will be depleted and the response is reduced. You can generally think about it as if your standard buffer starts with 50 and 50 of your HA and your A minus. If you remove some of this, maybe this gets changed to 30. You can respond by donating 10 over, and your new is going to be like 40 and 40. So like if you remove 30 of that, and you can be pretty resistant to that change. However, if you have a second buffer that only has 5 particles of each or 5 uh, molecules of each, you can't remove 30. You can't add more acid because you just don't have the capability to make that adjustment. You will fully deplete your conjugate acid or base. And so it's very much like you're thinking about magnitude of change. If you remove 1,000 minus 5 is still about 1,000, but 10 minus 5 is definitely not even close to 10. It's orders of magnitude. And so really you have to start thinking about this more abstractly and less in the physical realm of how much does it change. So you don't really want to dilute your buffers. They will just be less able to respond. Anyways, I hope this helps you understand buffers a little bit more and have a great night.